Hydraulic systems represent the most significant single improvement in machinery since horses were replaced by internal combustion engines. Hydraulic systems allow the operator to effortlessly exert thousands of pounds of force from where he's sitting. Hydraulics provide sophisticated control, improved performance, simpler operation, and increased productivity. This videotape will outline causes of overall hydraulic system failures, why preventive maintenance procedures are important. By establishing proper preventive maintenance procedures, you'll minimize hydraulic failure, which results in costly replacements and downtime. Machine hydraulic systems consist basically of four components: the power source or pump, the actuator or cylinders and motors, the control mechanism or valves, and the oil stored in the reservoir. The pump is the heart of the system. It accepts mechanical energy and converts it into a flow of hydraulic oil which moves throughout the system. The cylinder or motor is driven by the oil flow and uses the energy to do work. If force is applied to the pump, it forces oil into the cylinder or motor. The pressure of the oil pushes up on the piston and lifts the weight. The pump converts mechanical power to hydraulic power, while the cylinder converts the hydraulic force back to mechanical force. Valves direct the oil to the cylinders or motors, or can hold the oil in the cylinder between strokes. The reservoir stores the oil. It may have an air vent or a pressure cap, which allows air to replace oil forced into the pump by gravity and atmospheric pressure when the pump piston is retracted. All hydraulic systems are basically the same in principle. However, some become more complex to handle the multiple jobs placed upon them. The blood of the system is the hydraulic oil. It's been estimated that up to 70% of hydraulic problems stem from the use of improper types of oil or oil containing dirt, air, and other contaminants. Hydraulic oil is a highly refined petroleum product, usually containing additives, some to suppress unwanted properties and others to give the oil desirable properties. Hydraulic oil must serve three purposes. It must transmit power applied to it. It must provide lubrication for moving parts and protection for machine parts from rust and corrosion, foaming, and oxidation. Viscosity, or fluid thickness at a given temperature, is important for proper transmission of power. Most petroleum oils tend to become thin as the temperature goes up and thicken as the temperature goes down. If viscosity is too low, the oil too thin, leakage around seals and from joints is increased. If viscosity is too high, the oil too thick, sluggish operation results and extra horsepower is required to push the oil through the system. Viscosity also has a definite influence on the fluid's ability to lubricate moving parts. To assure optimum performance and service life from system components, use the right oil recommended by the manufacturer. It will contain only those additives required to control rust, foaming, and oxidation. Use of other oils may contain or lack additives which may shorten service life. And match, don't mix, is a good rule to follow in oil use and storage. Above all, buy quality. For your protection, buy oil from a reputable manufacturer that will stand behind his claims of meeting oil specifications. The lower its quality, the more it costs in the long run. Good lubricating qualities become even more important in many machines where hydraulic oil has a dual purpose: to operate hydraulic mechanisms and also to lubricate the transmission, differential, and other parts of the machine. Clean oil is very important in maintaining a trouble-free system. From the beginning, fire, water, air, and earth became the Earth's four major elements. Today, they have also become the major source of hydraulic system problems. Contamination, aeration, cavitation, and overheating are the results. Contamination is the most frequent hydraulic system problem. Even a seemingly insignificant amount of contamination during normal machine operation will cause poor equipment operation, component wear and failures, and eventually downtime. Each hydraulic system with the pump as its most used member consists of high-precision parts, often made with watchmakers' tolerances and clearances. Because of the small clearances in pumps, valves, and other moving parts, when abrasive particles enter these very small spaces, surfaces can be scored and honed, and clearances can be increased, reducing the effectiveness of the component. Clean oil will help hydraulic components deliver the best service life and performance. Contaminated oil only means problems. It's important to maintain clean oil. All good hydraulic oil, which comes in cans or barrels, is considered clean and free from contaminants when properly stored. When opening a can or barrel, make sure the area around the opening is completely free of dust, dirt, lint, or water. If a container or funnel is required to fill the system, whether at the job site or at the maintenance area, use only clean containers to carry and pour the oil. Barrels of hydraulic fluid should always be stored indoors. If that's not possible, store under cover out of the sun, on their side, not upright. Be sure the stopper is tight. If barrels can't be laid on their sides, tilt them slightly so water can't be drawn through the stopper. If barrels are stored in the sun, the hydraulic fluid will expand, forcing some air from a loose stopper. Then, as the hydraulic fluid cools off, it contracts, drawing rain, dew, or other moisture into the barrel. The water from these sources will mix with the hydraulic fluid and cause problems with the system. There are many ways contaminants find their way into the hydraulic system. Most systems contain a variety of contaminants produced during assembly or repair. Air in the machine's natural environment is another source of contamination. It doesn't take long for dirt and water to enter the system through cylinder rod wiper seals, a breather, pressure cap, or filler cap that's loose, lost, or carelessly removed. Make sure the system is properly vented or under proper pressure, whichever is applicable. Wear debris created during normal operation is another source of contamination. They include carbon and varnish from overheated oil, metal scraped off moving surfaces, particles from seals, and persistent emulsions. Bits of metal, pieces of seals and gaskets, and other abrasive particles will contaminate the oil. They'll also get caught on the edges of moving parts. Larger particles will wear off the sharp metering edges in valves or score cylinder and pump bodies. Smaller particles become trapped between closely fitted parts, causing them to stick or freeze completely. Other particles embed themselves in softer metals to grind away moving parts and seals, causing internal leakage and loss of efficiency. Many of these fine particles that cause abrasive wear are usually not visible to the eye. In comparison to human hair, the size of these particles is minute. Manufacturers work many hours and go to great expense to develop filters that clean out contaminants in hydraulic systems. Using a filter with improper micron filtration or filter area will greatly affect system life and response. Be sure to use the manufacturer's recommended filter. Will-fit filters that last longer may be allowing many minute particles to pass through the filter instead of being trapped. The filter may be cheaper, but in the long run more expensive. Change the filter or filter screen on a scheduled basis, at least as often as recommended in the operator's manual, more often if conditions warrant. Remember, the operator's manual only states the maximum time the oil and filter should be used. Good preventive maintenance procedures tell how often they should be serviced. Water is another contaminant that can easily find its way into a hydraulic system. Water vapor can enter the system through the reservoir breather, where it condenses into droplets. It may also enter through leaks in the system. When water is in the system, contrary to popular belief, it will mix with the oil. Because of the violent agitation, churning, and continual recirculation in a typical hydraulic system, the water and oil mix quickly. The water becomes homogenized and stays in suspension in the oil, giving it a cloudy, milky look. Slimy, sticky, pasty substances, referred to as emulsions, also form. They'll interfere with the normal operation of valves and other parts. Water can also cause vaporization at the inlet to the pump. The emulsion promotes rust, increases oxidation, which forms acids and sludges, and reduces the fluid's ability to lubricate moving parts properly. Overheating is another cause of hydraulic system problems. In an overheated system, metal parts expand. As a result, clearances around sliding and rotating parts may be increased, especially if dissimilar metal parts are used. Oil slipping through pumps or valves reduces efficiency and further increases the temperature of the oil. Overheating causes the hydraulic oil to break down. It results in the formation of acid, varnish, sludge, and reduced viscosity and lubricating property. Varnish and sludge clog orifices and cause sticking and jamming of close tolerance parts. The acid attacks metal, corroding it, resulting in accelerated valve, cylinder, and pump wear. Oil breakdown means equipment is operating with oil that doesn't meet specifications. It loses much of its film strength. Spotty lubrication at critical wear services occurs. Deterioration of oil that's too hot will cause accelerated wear and shortened service life in all parts of a hydraulic system. Heat buildup, in addition to thinning and breaking down the oil and decreasing system efficiency, will cause deterioration of seals, O-rings, gaskets, and other non-metallic components. It also increases corrosion. For every 18 Fahrenheit increase in the system temperature over the recommended system temperature, the rate of corrosion doubles on surfaces exposed to water and air. An overheated system is caused by incorrect, dirty, low, or leaking oil. Possible improper system pressures, a relief valve that's sticking or not properly set. Improper operation of the equipment caused by exceeding the relief valve pressure setting for excessive amounts of time during each operation. When doubt exists about the capability of a machine, consult its specifications and don't exceed these specifications. Higher pressure operation may contribute directly to faster wear and shorter service life for system components. An overheated system may also be caused by a malfunctioning oil cooler. Check the cooler to make sure airflow to the fins is not restricted. Paint, oil film, dirt, and debris will reduce the cooler's efficiency. Heat buildup can also be minimized by keeping all external surface components clean. A layer of dirt or mud may act as an insulator that interferes with heat transfer. Aeration and cavitation are also a source of hydraulic system problems. The presence of air and hydraulic oil can have a drastic effect on system performance and reliability. Air can exist in the system in any one of three modes: dissolved, entrained, or free air. Hydraulic oil at sea level normally contains up to 10% dissolved air. Low pressure on the suction side of the pump can bring dissolved air out of solution. Entrained air is present in the form of bubbles. Free air is trapped in a system but is not totally in contact with the oil. It's neither dissolved nor entrained, it's entrapped. Free air may be removed by bleeding the system. Aeration is the introduction of excessive amounts of air into the system, making the system spongy. Oil delivered to the pump can be aerated as a result of foaming due to low oil level in the reservoir. A restricted pump supply line may also be the cause. Check hose clamps to make sure they're not crushing inlet lines. Lines that are kinked, bent, twisted, rubbing, or too small for the pump. Using proper procedures, check for blisters, cracking, splitting, collapse, pinhole leaks, wrong fittings, or improper routing of the hose. Replace any that are showing deterioration. Don't wait until they fail. Hoses are the network that ties together the vital parts of a hydraulic system. Without them, the system can't function. Cavitation results from the high pressures generated as minute vapor particles in the oil collapse during compression. Cavitation can interfere with lubrication and destroy metal surfaces, and can cause higher than desired temperatures. Inevitably, cavitation leads to part wear and eventual pump failure. The effects of aeration and cavitation can be heard and felt. Noise is a good indication air is leaking into the system. In the case of aeration, it may build up gradually over a period of time and go unnoticed. Cavitation noise, however, will be a loud, high-pitched hammering sound that can start quite suddenly. Vibration can also result, which can loosen components, cause air and oil leaks, and quickly destroy system components. Prevent air from entering the system. Air can enter the system through small leaks in suction and pump inlet lines, through foaming in the reservoir due to low oil levels, lines, screens, or filters that are clogged and restrict the inlet flow of oil, or water in the oil, which promotes condensation. Establish proper preventive maintenance procedures. Check the oil. Make sure you use the proper oil. Keep it clean and change it at scheduled intervals. Check the system for signs of any leaks. Use the manufacturer's recommended oil filter and change it at scheduled intervals. Prevent any type of contamination, solid or liquid, from entering the system. Check pressures. Make sure they aren't excessive, and operate the machine for purposes intended. In short, use common sense. Preventive maintenance of hydraulic systems costs little. The best oil, kept clean, changed as frequently as recommended, and the scheduled changing of the correct oil filter are important investments you can make to avoid downtime and costly repair.